All right, so this lesson we're looking at mostly areas, and we'll eventually see how that connects to distances. But we'll start to look at one of the fundamental ideas of integral calculus, which is trying to determine the area under a curve, which again, if you compare it to which is one of the most fundamental ideas of differential calculus, which is finding the slope of a curve, the two seem fairly unrelated. And within a few lessons, we'll see how they are actually quite closely related. But what I have here are three different versions of the graph, y equals root x. You can see in red the graph of root x. And I'm trying to approximate the area between the x-axis and the curve in three different ways. And if you look at, maybe I'll focus on this. The expression on the left, I'm trying to approximate this area. Really, I'm trying to approximate this area that I'm highlighting in green, but with a series of rectangles. And so for this example on the left, all these rectangles have a width of 1 unit. So again, if we look at, zoom in a bit, I have 4 identical rectangles. They all have a width of exactly 1. So the area of each of these rectangles is very simple. It's 1 times the height. The height of each of these is set to be matching up with the left endpoint of the curve. So for example, this first rectangle, which actually has no height, is because on the left of that rectangle, the endpoint matches up with a height of 0, an output of 0 in the curve. Perhaps a little more straightforward is if I look at these other points. Notice the left of each of these rectangles matches up with that point I've drawn a little red dot at, which again matches up with a point on the graph of y equals root x. And so what I look at here, if I were to find the area of these 4 rectangles, or really 3 because one of the rectangles has no area, that would give me an estimation for this total area. It would definitely be an underestimate. I mean, if I compare that to what I'm trying to eventually figure out, which is all of this, I can clearly see those 3 rectangles or 4 rectangles is covering less than the total area I'm trying to figure out, but it's an estimate. Another way of approaching it is to find, again, 4 rectangles where the rectangle's height is set at the midpoint of each of these. They have the exact same width. Notice each of these, again, has that exact same width of 1. But this time, the height of each is set to the middle of these intervals. So if I look at these, this would be 0.5, 1.5, 2.5, 3.5. And I can see that estimate I think would make, in this case, a better estimate for this area than the previous example. I think that the area under this curve is better approximated by, in this case, these 4 rectangles. Although it's hard for me to tell if my estimate would be a little too high or too low by just looking at it, but it'd definitely be a better estimate in this case. Please don't think that midpoints will always be better. And the other example is when we have all our rectangles set at the right endpoint. And again, the right side of these intervals. All right, so first let me explain. We can just see now a visual of how all of these would estimate the area of this region. The left endpoint in this case would definitely be an underestimate. The right endpoint would definitely be an overestimate. So in this case, that middle, using the midpoints would definitely be the best. But eventually, I don't want just an estimate. I want to be exact, the exact area of this. With that said, though, let's connect this back to sigma notation. And so what I have here is the sum of all values of root x from 0 to 3 times 1. Now, what does this represent? Well, this root x times 1 represents the width and height of each of these 4 rectangles. Root x being the height, and maybe I'll label that right there. That represents the height of any of these rectangles, and 1 is the width of any of these rectangles. And again, area of a rectangle, height times width, length times width, however you want to look at it. So they all have the same width. It's the height that's changing every time. And so in this case, if you look at the 0 to 3 part, that's because my endpoints, my first endpoint's at 0, 1, 2, 3 is my last endpoint. And so that's why this particular sigma notation connects back to that visual there. So let's calculate this. And a calculator will quite soon come in handy, but let's remember how we read this. This really means the square root of 0 times 1 plus the square root of 1 times 1 plus the square root of 2 times 1 plus the square root of 3 times 1. And then we stop there. Because we're starting at 0, we're ending at 3, as you can see from the sigma notation. All those little 1s I don't really need. So really, this is the same as 0 plus root 1, I don't need the root 1. 0 plus 1 plus root 2 plus root 3. And if I decimalize that, I get about 4.15 square units. And again, I can tell, compared to the actual region underneath here, that is an underestimate. And so keep in mind that sigma notation we see there, what we have here are the areas of individual rectangles, the height and the width. The width is a constant, in this case always 1. The height is what's varying, and the height, though, is dependent on that curve, in this case root x. And again, to get this 4.15, I just typed 1 plus root 2 plus root 3 into a calculator. All right, so let's do the same thing for these other estimates. Now, I can see the midpoint one will definitely be more accurate. But how can I write this in sigma notation? Well, one thing you may or may not recall about sigma notation is you can't do this. I can't start at 0.5. By convention, I have to start at an integer. And so I'm just going to start at 0 again and go to 3. And my width will be unchanged. The width is still 1. What's changing is my height. It's not the same as, my first height is not at 0. My first height's at 0.5. The next one's at 1.5 on the x. 2.5, 3.5. So it's always, I can say, the same x values as I had for this example right here, but plus 0.5. So my height will be, I can say, the same as root x plus 0.5. To give myself a little bit more space. And again, what I've just highlighted in yellow there, that represents, again, the height of any of these individual rectangles. So notice, if you work your way from 0 to 3 for x, you get 0 plus 0.5, 1 plus 0.5, 2 plus 0.5, 3 plus 0.5, which matches up with the midpoints of each of those rectangles. So there's my expression in sigma notation. Again, the convention of sigma notation, you can't have, or I'll say it the other way, you must have integers or whole numbers for these. And so with that said, now to calculate this, it's fairly routine. So everything's times 1, so all I really need to do is, I'll kind of go down here, really have the root 0.5 plus root 1.5, and so on, all the way to root 3.5. All those is times 1, so I'm not going to bother writing that down. And you decimalize it, you get about 5.38. Notice, not surprisingly, it's a larger number than we had from before, because I knew this was an underestimate. But the most important part is realizing how really, again, I have all these little rectangles I'm adding up. In this case, they all have a width of 1. And again, the height is varying. In this case, the height is based on the midpoint. And because each had a width of 1, the midpoint was 0.5, 1.5, and so on. And lastly, the right endpoints. So again, I can set this up in sigma notation. Now, if I want, I could start at 1 and go to 4. That's perfectly valid. If you look at these 4 points, my first point is at 1. Right? Honestly, in isolation, I think that's the best way of approaching it. But just to make it kind of compare to everything else, I'm going to still go from 0 to 3. But then my first height will be not x, it'll be x plus 1, all times 1. You may recall with sigma notation, there's always more than one way of expressing it. But in this case, again, the width of 1 doesn't really matter. Multiply by 1 doesn't change things. So if I actually work this out, in the end, I get root 1 plus root 2 plus root 3 plus root 4. Those are the heights of those 4 rectangles. All times 1. Without a calculator, 1 plus root 2 plus root 3 plus 2, decimalize it, get to about 6.15 square units. And so just from looking at these visuals, I can tell that this is the best estimate so far. I can tell that 6.15 is an overestimate. If I look at that visual compared to what I'm trying to figure out, I can clearly see that's an overestimate. And I mentioned before, this 4.15 is an underestimate. So what would make this better, though? Even if we're still estimating, how can I make these estimates better? Well, what if I have more rectangles? I mean, 1 is a lovely number, a width of 1. It's a nice number. But if I had more rectangles, I could approximate that area better. And that's what we see in this next example. Same idea. The curve you see is root x. But this time I have 8 little rectangles based on midpoints. And so each of these rectangles, here's 1, 2, 3, and 4. I can just see quickly, by having 8 little rectangles, the area of this region compared to the area of these rectangles, the two are getting closer and closer. I can actually see that this particular estimate of these 8 rectangles is probably going to be a little bit larger, but it's getting pretty good. So how can I approach this? Well, in this case, let's just calculate that let's find that estimate. And so how can I find this estimate? Well, if you look at the diagram I gave you, I can see each of these rectangles is from the midpoint. But again, this is 1/2 right here. This is 1.5 right here. So these midpoints are at 1/4. 0.75, 1.25, 1.75, 2.25, 2.75, 3.25, 3.75. Those are my, those are the heights of each of these rectangles. The square root of each of those values I just said, because those are the x values we're looking at. And so to find the area of these 8 rectangles, I need to take the square root of each of these x values, 0.25, 0.75, or really I need to find the height of each of these rectangles, but then multiply by 1/2, not by 1, because each rectangle has a width of only 1/2. That's it. Because they all have the same width, I can really just add up all the heights and then just multiply by 1/2 at the end. It's the same thing. However, in the end, yeah, I have a fair number of little steps here. For example, that first rectangle, the one I'm going to highlight in yellow right here, that has a height of the square root of 0.25, because the x value of that midpoint is 0.25, and the height is based on the square root of the x value. And so, if I want to find this total height or total area, I'll say it's going to be root 0.25. And again, I could go times 1/2 and do the same thing for every single one. The next one would be root 0.75 times 1/2. Or what I'd rather do is just add up all the heights and then multiply everything by 1/2 at the end. So I get the square root. Actually give myself a bit more space. So 0.25 plus root 0.75 plus root 1.25, all the way up to root 3.75. And so that represents all these heights. But again, they're all being multiplied by 1/2 because that's the width. That will represent the total area of all those 8 little rectangles. And yeah, type this into a calculator, blah, blah, blah. Type it in. You should get about 5.35 square units. So I now know that that's my best estimate yet. I compare it to what I had before. I had 5.38 for my midpoints last time. So from going from 4 rectangles to 8 rectangles, I got a better estimate. So what if I want to make it even better? Well, what if I made each width 1/4 instead of 1/2, which means I'd have 16 rectangles. Or what if I made it an 1/8, and so on. The skinnier you make each rectangle, the closer and closer our estimation gets to being the actual value. And again, the whole idea is eventually we're trying to figure out understand the idea about how we can find the area of sort of any curve. And so the basic fundamental idea right now is it's realizing, okay, yeah, it's a bit annoying to find the area of all these little rectangles. But the fundamental idea is that the more rectangles I have, the better my estimate gets. And there's no limit to how many you can have. Which leads us to the idea is, what if you had an infinite number of infinitely skinny rectangles? My first examples, I had 4 intervals. Then I had 8. And I mentioned, what if I had 16 intervals? Or what if I had 1,000 intervals? Or what if I had 1,000,000 intervals? Or what if the number of intervals approached infinity? The more intervals we have, the skinnier and skinnier and skinnier these little rectangles get. And the more and more and more our approximation approaches the actual exact area. And that idea leads us to what we call the Riemann sum. And what you see here, this visual here, is the idea of what I was just describing. Imagine this interval from 0 to 4, like we've been doing every time, for the graph y equals root x. But now imagine if we just kept making these rectangles skinnier and skinnier and skinnier, eventually it wouldn't be an estimate at all. If the number of rectangles approaches infinity, that means the width of each rectangle approaches 0, and which means the area you get is no longer an estimation. And that idea, which is fairly abstract, is what we see kind of written right here. So we have a sigma notation, but this time set up slightly differently. Again, this right here still represents the height of each rectangle. That's still height. And this is width, the change in x. That's my width, which again is approaching 0, the more and more rectangles you have. That's my width. This is height. And again, the root x is because this is all based on the graph of root x. That I, right there, or right there, that represents the interval number. Like the rectangle, the first rectangle, the second. And we're going from I is going from 1 up to some number. But the idea is, what if, that's essentially the number of rectangles. My first example, you can think of the first example I gave you today, that was a 4. And the second example, it was an 8. Well, the idea is, OK, what if we eventually, that approaches infinity? That's what I was kind of mentioning before. And as n approaches infinity, then the width, again, approaches 0. And so you get infinitely many, infinitely skinny rectangles. And everything I'm describing is what is being this is the notation for it right now. And again, it's called the Riemann sum. It's sigma notation, but with an infinite number of rectangles. And this here represents the sort of interval we're looking at. Because if you don't have this part here, if I erase this for a moment, the 0 to 4, suddenly we don't know where this interval starts and stops. And that's why we have this little interval right here. So that represents the interval that we're trying to find the area of, 0 to 4. Now in reality, again, this is more just about notation. Because just given this, if I give you something like this, a good question is, OK, how do I calculate that? Well, eventually we'll get there. But right now it's just about understanding how to read this and really what this means, all these infinitely many rectangles that are infinitely skinny. And again, don't lose sight of what I keep highlighting here. This first part here in yellow, that's the height of each of these infinitely many rectangles. And the root x this time, sorry, not root x, delta x this time. The change in x. That's the width. And the larger n is, the skinnier those rectangles are. And the larger n is, the more accurate this is. So with that said, what if we had a sort of an applied problem, what would the area represent? Because a perfectly good question is, why do we care about finding this area? Like, what does it represent? And depending on the function we're looking at, the area can represent something actually quite pleasant or quite important. And it's pretty easy to overlook that. So before I move on, again, with this Riemann sum here, the main idea is just understanding how to read this and what it's kind of describing. In terms of actually calculating it, we won't get there for this lesson. So with that said, here I have a graph showing you the velocity in meters per second of someone driving a car for 30 seconds. And these little points are every 5 seconds. So we can see at time 0, they had, that's the moment they hit the accelerator. That's the instant they hit the gas, or whatever. 5 seconds later, their speed was 8.06 meters per second. 10 seconds after the start, 11.94 meters per second. Again, and so on. So that's what this is showing you. Okay, the velocity every 5 seconds. So what I want us to do is use the method of right endpoints to estimate the area under the curve. And then, what does that area represent? All right, so method of right endpoints means I want to create a bunch of rectangles. I'm going to go with rectangles that are 5 seconds, 5 units wide, just because that's what our data is given to us. And so if I'm using right endpoints, for example, my first rectangle will look something like this. The width is 5, the height is 8.06. And my second rectangle would be right here. And my third, and so on. So I'm visualizing the rectangles we have here. And since I've asked you to find the area of the rectangles using right endpoints, that's why every 5 second interval I'm looking at the point on the right, not on the left. And so, well, that was a pretty bad line there. Let me just grab my highlighter. So if I just look quickly without doing any calculations at my, what is that, 6 rectangles, I can see pretty quickly that the estimate I'm going to get is going to be an overestimate. Especially in the first chunk, my rectangles are always larger than the actual area. So again, if I look at these are my 6 rectangles that we're going to figure out the areas of. Add those all up together, I get an estimate for the area under this shape. But again, what we're trying to do is use that to estimate this region here. Right? Representing estimate of that region there. It's a lot of highlighting on top of highlighting, so let's just stick with this. All right, so let's find this area, which again, I can tell is going to be an overestimate. But then after that, really the most important thing to me is what does this area represent? So I have 6 rectangles. The heights are all the right endpoints. So for example, the first rectangle has a height of 8.06 units. The second rectangle has a height of 11.94, 22.78, and so on. And so each of those has a width of 5. So I could, for example, that first rectangle, I could go 8.06 times 5 plus the next rectangle, 11.94 times 5, or I can add all these up and then multiply by 5. And that's what I'm going to do. So the area of all of these will equal 5, that's my width, times all these many heights. All right, those are all my heights times the common width of 5. Multiply all this together. And yeah, like I said, I find it a bit annoying typing all these things in. You get about 586, I think, 0.1 square units. So that's my estimate for that area. That's the area of those 6 rectangles, which again, I know is a little bit more than the actual area under that sort of curve. However, what does this number represent? What are the units? Well, for that, let's think about what we just calculated. All of this here represents the height. And what were the units of the height? The height was velocity. My y outputs. So all of this is meters per second. And the 5 represents the width of each of these, which is 5 seconds. So it's seconds times meters per second. Well, seconds times meters per second, the seconds cancel out. So my units are just meters, which means the units of this area are meters. Not meters squared, not square units, not anything else but meters. The units of this area we figured out are meters, which gives us a very strong indication about what this represents. This represents the total area, this represents the total distance we have driven in the first 30 seconds. We traveled just over half a kilometer. That's what that represents. That's the total distance we've driven. It is an overestimate because, again, all these regions here are greater than the actual curve, even though it's compensated a little bit by these little chunks here. But it's an estimate, and it's an estimate of the total distance we've traveled. So this represents the total distance traveled, or total displacement, I'll say. After 30 seconds. And it's not a coincidence that we were looking at a velocity function. And when we found the area underneath it, we got displacement. And if you go this way, velocity is the derivative of displacement. We've seen that many times earlier in the course. But now we're starting to go the other way. As we saw, and again, you may have already realized this, but displacement is the antiderivative of velocity. And so we will start to see how derivatives and antiderivatives come back into play with this. Even though right now it seems like we've kind of gone off topic, just all these rectangles we're adding up. All right, so with that said, before I finish this off, let me do one thing that I don't recommend you do in your notes. But I should say as well, if we're trying to estimate this area, because in the end, I'm trying to estimate this area under this curve, I don't actually need any complex math. If I break these up into some triangles and rectangles. Then I could get the exact value. It would be fairly annoying. There's a lot of rectangles and triangles. But then I'd get the exact value for this particular graph. However, again, this estimate here is good enough for now. All right, and that's where I'm going to stop.